Yeah, so very excited to have Jacob, who is one of my fellow PhD mates from CMU. He works in Aditi's lab, and he also works with Christina, who is also in Aditi's lab, and Rico. And he has done some very relevant work, at least for the conversation that we have. We've already talked a lot about overtrained language models and how to fine tune on our paper channel. He also worked on echo embeddings, which is like central to everything we do. And so we're very excited to hear more and get his pulse on where we are going forward with functional pre-training or like what are the best embeddings to use and everything from there. Yeah.
Great. Yeah, so I'm going to be talking about two pretty different topics. And so I've kind of organized it into like a part A and a part B with no particular transition between them. So I figure we spend like, less than half of the time doing each of them and then chat.
Sorry, Jacob, do you mind muting?
We're not going to make you try to act like there's a clear.
Right, yeah, I think I figured.
Hey, Jacob, do you mind muting the microphone on your side of things? I think it's echoing.
Oops, sorry, I meant to do that. Yeah.
No worries.
Can you hear?
Yeah, we can hear fine.
Okay, so I want to introduce, all of you are well aware of the general LLM training paradigm that we have today. And I'm sort of simplifying a little bit because I know there's maybe mid-training and other types of training that one might do. But generally, it's organized into two setups, sort of a pre-training stage and then a fine-tuning stage. And in particular, oftentimes the pre-training stage, you're training on, of course, the entire internet that your company is doing. And then at the fine-tuning stage, you're training on some sort of limited data to try and adapt to a downstream task. And so I think the thing I want to sort of challenge today is what I'm going to call the central dogma of modern ML, which is that if you scale compute sort of naively, you're going to improve performance. And in fact, it's been quite challenging for people to come up with cases where this is not true. Of course, we get like the Kaplan-Nadal scaling laws that says that if you scale compute by scaling both the model and the data size, then you're just going to improve performance. And then there was even a line of work, which I have some slides that I think are hidden here, on inverse scaling tasks, where if you scale up compute, people were finding a couple examples of tasks that would decrease in performance as you increase the amount of compute. But then they found that it's U-shaped in the sense that if you continue to scale up compute, often these tasks end up improving performance, pretty much no matter what. And so, originally, back in the day, 2020, people were scaling both model size and data at the same time. There's a lot of work on finding sort of compute optimal regimes. But these days, I think that scaling data alone is a very common paradigm, simply because one wants to have a language model or a general model, foundation model, that has a relatively fixed inference time cost. And so there was this paper in 2024 that showed that you can also do scaling laws on what I'm going to term it as overtraining, where simply you increase the amount of data without increasing the amount of compute, and you get consistent performance that you can predict. And so I want to argue that this is sort of the default strategy. This is, I tried generating these with ChatGPT. It's gotten worse. I can't generate this anymore.
Oh, do you think it's because it's overtrained?
Yeah, but yeah, you can see that in the span of a little over a year, you get a 15-fold increase in the number of tokens that at least the Llama team is using to train our models. And so what do we really want if we want to be able to then adapt our model to a downstream task? So I want to claim that there are basically two different desiderata that we want. One, we want adaptability. That is, we want to be able to do well on the actual task that we are adapting our model for. And second, we want robustness. And in this case, I'm referring to we want to maintain existing capabilities. And so when you train for, say, vision language model, you want to incorporate some ability to reason with images. You don't want to lose your general reasoning capability or your fact capability. So let me give you an example of what this might look like in practice. And we're going to sort of use this example, at least beginning of the talk, just so we can talk about concrete metrics to understand what is a concrete way we can measure adaptability and robustness. And it's really simple. One, adaptability, you can just measure what I'm going to sort of call the in-distribution task, which in this case will just be response quality because we're doing instruction tuning. And so you can use something like alpaca eval in order to measure how good are your responses that you get when you sample a language model to some instruction tuning data set. And the second thing, we can measure robustness, again, the performance on unrelated tasks, simply by measuring performance on unrelated tasks. And so we can just look at generic LLM benchmarks. And so the benchmarks I'm going to consider are relatively old, simpler benchmarks, just because we're looking at smaller models, which we'll talk about, like ARC, Pika, HelloSpy, etc. And our first major claim of this work is that overtraining can hurt adaptability. And so again, remember, adaptability is the alpaca eval performance in this particular case. It's what we're actually training for. And we observe that if you take, in this case, all mode checkpoints, and we'll get back to why we're taking checkpoints and how we can sort of control some of the issues that causes, that as you increase the number of pre-training tokens, initially your performance will improve, but eventually your performance will start to decline. So the fine-tuned model response quality eventually decreases as you increase the amount in this situation. Secondly, overtraining can hurt robustness. So what does that look like? Well, if we again measure the performance of out-of-distribution tasks, out-of-distribution here refers to out-of-distribution with respect to the fine-tuning task, then again, the performance will initially improve and then eventually decline. And so what you're seeing here is, again, over all mode checkpoints, we're going to fine-tune each checkpoint for instruction tuning. We're going to do all of the hyperparameter tuning for instruction tuning. And then what we're going to do is measure this performance in these like unrelated tasks. Yeah.
So are these values being compared to like and like so you're taking a overtrained model and then plotting this, right? So are you able to compare these to a non-overtrained model, which is then fine-tuned and then see the difference?
Right. So actually, this is a really good point. The way I guess I'm going to talk about overtraining in general is to know sort of what is an overtrained and a not overtrained. I am not doing sort of the obvious thing where you're comparing it to like chinchilla, like compute optimal regime. In particular, overtraining I'm going to define as just extending pre-training. And so there will not be a specific point at which point a model is considered overtrained or not. It's going to depend on the data set. Really what I mean is that there sort of exists this peak somewhere for an individual data set, for an individual fine-tuning data set, and it turns out also for an individual eval data set, where for this particular combination, like pre-trained model, evaluation data set, fine-tuning data set, you get sort of an overtraining point where you go beyond that. And so what you're looking at the beginning of training is, I guess, like for this combination, an undertrained model where performance is improving as you increase the number of tokens. And at the end, you could call it overtrained. But I agree with you that like conceptually, there's not like a clear definition of what is an overtrained model here.
I don't know if it's clear. The x-axis is pre-training tokens, so like that's the. I don't know if that was your question. So it's like actually like I don't know. Maybe that's what your question.
Yeah,
Right. So we're all gonna x-axis for this entire talk will be pre-trained.
It's like fine-tuning at each.
Yeah. So these are different. Here's different checkpoints. Later we'll pre-train.
But each checkpoint is post-trained.
Each checkpoint is post-trained.
Right.
Yes. Yeah, and
Would you not suggest that perhaps post-training needs to be adjusted to the model depending on how much data is seen in pre-training?
So we do individually for each one.
Okay.
So we're kind of giving it and actually it turns out that the hyperparameter tuning is a really key element of the story, which we'll get into later. But like for this particular graph, we're doing instruction tuning on, there's a few different data sets, which I think this one is the Anthropic HH, but and so for each individual checkpoint, you're going to tune it to do as well as you possibly can in terms of response quality. Individually. So I'm just going to like give the definition. I'm going to call this term sort of catastrophic overtraining when you extend the amount of pre-training and then that causes your performance to decrease one way or another. There's like sort of different instances of this. And so the question we're going to at least try to address in the rest of this talk is sort of when does it happen and a little bit of why. And so a key things to keep in mind, I don't think we're going to actually answer fully any of these questions, unfortunately, but like sort of which data sets should this happen to, like how much overtraining would you expect to start to see the decline in performance, and like at least to some extent, why does this happen? So the obvious strategy that one might take in order to try and understand some of these questions, especially which data sets and how much overtraining, is just to try a bunch of things. Okay, so if you do that, I'm not going to make you like look at this graph really closely. I mean, we can ask questions about it later, but in general, here we're like sort of having the same setup as you saw before, instruction tuning, this like Olmo model checkpoints, and also on the bottom we do a different thing, you know, multimodal fine tuning, so DLM training. And an important takeaway here, which don't have to look at it, but I'll promise you, is that not all eval tasks show catastrophic overtraining. And so there are some eval tasks where performance is sort of strictly increasing, at least at this level of overtraining. And so another thing is like how much overtraining, well, if you scale up the model size to almost 7B, or this other open source one is LM360 Amber, which is another 7B model, what you find is that you do not get this overtraining effect at all. And so just some napkin math. We can sort of estimate, well, I mean, I don't want to claim that the tokens per parameter, which is like the number of pre-trained tokens divided by the number of parameters, is going to be the exact metric. But if it were a reasonable metric, then Olmo 1B, which is the model that we're at least for now seeing this effect on, is way more trained than 7B, the other two 7B models. It's like, you know, something like 6 times. And so the Llama 3 models are kind of getting up there in terms of just this linear tokens to parameter ratio. I've heard anecdotally that people have had trouble training Llama 3. I don't know how true that is, but in theory, yeah. That's sort of the inspiration originally for this problem. So second strategy is, what if we can understand this in a sort of a controlled setting? And so we can, so now we're going to pre-train our own small models. Again, we're using academic compute, so we'll do 30 million parameter models. And in general, we're going to fine tune on language modeling tasks. So this, you call this continued pre-training if you want to. And our evaluation is just going to be the original web data perplexity. That's sort of our pre-training data set perplexity, held out, but nonetheless ID. And the adaptation evaluation is going to be whatever fine-tuning tasks we're going to look at, which there's a bunch of them. This could be like, you'll see GSM8K there. We're not training to do well in math. We're training to model the language modeling part of GSM8K. And so you can see that in this setting, we, again, on the x-axis, have the number of pre-training tokens. You'll observe this catastrophic overtraining effect, at least some of the time, both for this robustness metric, which is essentially how well will you retain capability, and also this adaptability metric, which is how well you can adapt to the downstream tasks. And this is after a very extensive hyperparameter tuning for each individual checkpoint. And so a couple things to like notice here is that there's sort of a lot of noise, and we'll get into that. We'll see much cleaner curves very soon. And also it doesn't really happen for every setting. Again, sort of similar to what we saw before. And so one question that we have is, can we sort of explain this a little bit better? We're going to focus for now on the robustness setting. So how well can you retain existing capability? In my opinion, this is the much more salient effect. And also the one that we can sort of understand a little bit. And there's also some amount of literature on the adaptability, which people would call loss of plasticity, if you want to search for that. This is like an RL, continual learning term. So we'll focus on this, so just sort of the novel part for language models.
Actually, can you go back to this slide? I think there are a lot of words and I'm just trying to map. So the pre-training happens on C4?
The pre-training happens on C4.
And the fine-tuning happens on the thing at the top of
Yes.
it, so GSM. So the idea is that if you pre-train on C4 and fine-tune on GSM, then C4 perplexity goes back.
That's right.
And the ID perplexity still goes down.
That's right.
But in Trek, the even adaptability is worse. So you can't keep, like, the more you pre-train on C4 and you fine-tune on TREC, its own fine-tuning capability also.
That's right. Yeah. That's exactly right. And so a couple things that you might have in mind. One, I mean, I talked about we do hyperparameter tuning for each individual checkpoint. Another one you might be thinking about, so the reason why we're switching to a smaller model as well is so that we can do the full training process. I don't know, like there was some, I guess, lore about the Kaplan papers where the Kaplan scaling laws had a bunch of issues, in part because they did a single pre-training run, and that turned out to have, there's some learning rate annealing effects that sort of caused their results to be incorrect. I think this is part of the reason why Chinchilla is different. Yeah. And so in this case, we're annealing sort of every checkpoint identically, which is to say we're using a cosine annealing rate, and we're like seeing the full, full cosine decay to the end of the checkpoint. So you can think of this as like models have been trained to each individual level of pre-training individually.
Sorry, I realize, is there a difference between, so each column is a benchmark. What's the difference between the top and the bottom evaluation metric?
Yeah, so the top is going to be our web data perplexity, which is to say we are not fine-tuning on web data. We pre-train on web data.
Okay.
Now we're fine-tuning on, let's say, GSM-AK as a language modeling task.
Yes.
And so the top is going to be our web, like how much, like you can think of it like catastrophic forgetting would cause us to forget some amount.
Okay.
And so we'll measure like how much do we forget.
Okay.
And then on the bottom, it's how well did we actually do at our language modeling task for GSM-AK. So like how well do we fit the GSM-AK validation set?
I see.
And then on the top, like because you have catastrophic forgetting, you are going to do worse than your base model no matter what.
Yeah.
The claim here is that you will do even worse if you continue to pre-train for longer. So if I don't know, yeah, the mouse here. If you were to also plot the pre-trained model, it would continually go down on the web data perplexity. It would like have a curve like this, and then so every point you get, or maybe it would start like this and then keep going down. And so you have this gap here that's getting kind of bigger and bigger as you continue to pre-train.
So I'm sort of surprised like that, Sika does not show this, like basically you're either going to, have forgetting or you're going to be, you're gonna have problems either with the pre-training or the fine-tuning distribution, depending on the interaction between how much you pre-trained and whatnot. But like, I feel like there's maybe something that is not captured here, which is like this similarity between your fine-tuning and pre-training distributions. I would expect that Sika, the reason you don't see a U-shaped effect on either of them is because it is more similar to the pre-training distribution than any of the other tasks. But also I didn't do these experiments, so I don't know if that intuition is valid or not.
That's exactly. I think that's exactly right. So we have some theory on like kind of a linear setup that does show exactly like there's some notion of similarity in the sense that exactly captures how like the fact that as you become more dissimilar, you'll start to see this effect. So I think that's exactly right. We don't have. I mean, it's hard to do on the. I don't know how to do that on like actual real data, like measure the sort of similarity between two data sets. Maybe you do. I'm not sure. Yeah.
Some approaches you could take, but
Yeah.
I don't want to distract.
Yeah, I know. But I agree. Intuitively, I wasn't planning on talking about the theory, but if we wanted to at the end, we could.
Yeah.
I have slides on it. They're hidden.
Oh, nice.
So when does catastrophic overtraining occur? Especially with, again, a focus on robustness. And so we're looking at the pre-training perplexity here, not the actual adaptability. We'll sort of ignore that for now. So let me give you the intuition that I have in my mind. So there's something we know. This is sort of the central dogma I was talking about. As you increase the number of pre-training tokens, your base model perplexity is just going to get better. At the same time, something that I'm going to call sensitivity is getting worse. And so in particular, the model is going to become more brittle to changes in its parameters. And so we'll like look at what that actually is in a second. But intuitively, sort of if you imagine that if you are then going to change the parameters somehow, if you are brittle to these changes, then looking at their final model complexity after you change the parameters in some way, you fine-tuning or adding noise, whatever, any sort of change the parameters, you're going to get this U-shaped curve where initially, as sensitivity is very low, your model is just getting better even after changes, right? So it doesn't matter that you change the model a little better. Whereas at the end of this graph, your model is going to get worse because the sensitivity term sort of dominates. So this is our intuition. Fine-tuning has a lot of complexity, so let's start with something simple. Let's just do Gaussian perturbations. That's really easy. So let's measure, this case we're going to call sensitivity is going to be the amount that your perplexity increases. So this is catastrophic forgetting. If you're comfortable with that, you can think of the delta perplexity as just amount of catastrophic forgetting as a function of pre-training. And so each color, like a single line, sort of represents a certain magnitude of perturbations. So we'll say that intuitively, larger perturbation, more forgetting. You should see like as you're increasing perturbation, you can see these like curves are getting progressively higher and higher. That's intuitive. But at the same time, as you pre-train for longer, your sensitivity is increasing.
So here, the scale is the size of the perturbation that's added to the weights, I assume.
The color is
The color,
size.
sorry,
Yes,
yeah,
yes.
But one question I have is like, are we sure that like the weight magnitudes are not also changing over training duration? Like, should like, would we not want to account for like weight magnitude, because like, if like during training you've got some like weight decay and then the model weights are getting much smaller, the same innovation could be like much larger relative to the model size.
Yeah, great question. So we also, I don't have it here, exact same graph, you divide by the weight norm.
Okay.
Same thing. Yeah, same thing, identical graph. In fact, it actually turns out that the weight norms in practice don't change as much as you'd expect them to. In fact, a lot of them get, so some weights will get bigger, some weights will get smaller, you know, just a bunch of things happen. So yes, it is not the weight norm itself.
Right.
Yeah. Right, and then so based on intuition, I mean, this is sort of just like adding back the actual final perplexity. You can see that you get the U curve. I should pause because this is sort of like, I mean, the rest of everything else is just going to be based on this. Are there any like clarifying questions about this?
I have a question. So on the right plot, basically adding a lot of noise is bad. And I guess maybe you're about to tell me, but like, how are we going to get that same like U-shaped behavior of the like light line on the right plot from continued training? And like maybe you're going to talk about this, but another thing I'm curious about. So you mentioned earlier that like, oh, it seems like counting the number of tokens per parameter is a good proxy for like understanding how like excessively pre-trained something is. This seems to suggest that do you have ways of like, if I gave you a model and I didn't tell you about anything about how many tokens it's been trained on, is there ways you can look at the weights or like query the network to like try to understand how pre-trained it is?
It's a really good question. I think that like it's a little bit hard. I don't have a clear answer for you. One thing that this is sort of related to, which one can query the model for, is sharpness. So this will be like the second order approximation of when you change the weights, how much are you going to degrade the model under whatever loss. And so that's something you can look at, and you can sort of decide, okay, if I think I mean, it's a little bit hard to decide, like when I have a fine-tuning perturbation, like how big is that going to be, in what directions that might be hard. But if you sort of know that, at least know vaguely what it's going to look like, you can just like look at the sharpness and say, if I were to move my weights this much, my pre-training loss is going to go back up this much, and that'll tell you something.
So then does using sharpness aware minimization reduce the sort of pre-training dependent scaling of the perturbation effect here?
That's a really good question. I don't know. I would guess, I can imagine it would. I'm not sure though. I think there's a lot of things one can do. So another thing like one can do in general to reduce the sharpness is just to increase the learning rate of your pre-training. We didn't really do that many experiments like with exactly how this effect works. One thing that one could probably do if you want to avoid this effect entirely which is sort of in a slightly different, like subtly different setting, which is that if you keep your pre-training learning rate sort of constant, and then you just train from that checkpoint, that I would guess works. I have some like sort of tentative experiments that say that can help a lot. One issue with that for our setting is that this model that you've released that has a high loss is really terrible at everything. And so there's like no sense in which you actually get any like improvement. So if you were a company, if you were Datology and you want to release your model and you want people to use it, you'd also then have to release a bunch of your training data too, so that they can enable it themselves. And that's sort of impractical in a lot of cases. And so like we're kind of looking at the case where you already have like a high quality yield model. And sharpness, I think to some extent is hard to avoid in that situation.
Indeed.
Yeah. Okay. Yeah, please feel free to stop me and we can go back to. But like just in your mind, I guess the picture I want to have is sort of this like, sharpness related one. Like our thing's a little bit more like global than sharp. We have sort of an appendix thing that says that like if you actually track what the literal second order approximation of the loss is, it's not a very good predictor of the effect effect we're looking here. Our effect is like much stronger than what the sharpness itself would predict, but you can kind of imagine it as sort of a sharpness thing where you can look at like your loss and say like early in pre-training, we'll say where our theta, which is like where we pre-train currently is sort of a low loss, and then you perturb it by a constant amount, and then you get to a slightly higher loss regime early in training. Whereas much later in training, you're at very, very low loss. So that'll be the center of the right one. So you're getting better progressively, but that same fixed magnitude perturbation is going to cause you to increase your the loss more. It's more sensitive. And so this picture sort of seems reasonable, but what's wrong with it for fine-tuning? It's almost right for fine-tuning, except the problem is that fine-tuning isn't necessarily fixed magnitude. Two different checkpoints could potentially give you two totally different fine-tuning perturbation vectors. Like maybe early in training, everything is just, I mean, like maybe the weight norm is bigger, and so like you have to just move further no matter what. And then later in training, the weight norms are smaller, and so you just move smaller. So we can sort of control for that by just asking what if the fine-tuning were fixed magnitude. And there's sort of empirically a very natural way to do this, which is that if you train with a fixed learning rate, but what by that I mean is that you train with the same learning rate for each checkpoint. You don't tune it, you just pick a learning rate. That's my learning rate. And sorry, let me clarify. We're gonna pick sort of like the hyperparameter. You can do annealing or whatever during fine-tuning. You can change your learning rate during fine-tuning, but we're just gonna pick like the max learning rate in our for fine-tuning. So this fine-tuning learning rate, if you let it be fixed, you'll get back to this like Gaussian intuition that we have where you get a fixed perturbation. And in this setting, you see these relatively clean curves, where again, like you can this is sort of analogous to the same plot we just saw a second ago. Now in the perturbation is just a fine-tuning one instead of a Gaussian. So you get this sort of increase in the sensitivity that's like the left, and then you get this together this like pretty clear U-shaped perplexity again with this sort of fixed size perturbation that we see during fine-tuning. And so now the question is, well, what happens if you're willing to tune the learning rate? So this is tune the fine-tuning learning rate for each checkpoint individually, which is something you would naturally do. And this is what gives us the variability in all of the pre-training tasks, or the fine-tuning tasks that we looked at earlier. So for example, what if there's some inductive bias of this like green learning rate that just gives you really good performance, no matter what checkpoint you're at? Well, then if you tune the learning rate properly, you're going to see this U curve where performance eventually declines. So if you need an inductive bias of sort of a larger learning rate for all checkpoints, no matter what, for the fine-tuning task, then you're going to end up seeing this catastrophic overtraining effect. At the same time, let's say your pre-training task and your fine-tuning task, as you continue to pre-train, are getting closer and closer together. Maybe you can get away with using less of this large learning rate inductive bias. So you can like sort of decrease the learning rate that you're using every single step. Maybe in the limit as you pre-train infinitely, you can just not fine-tune at all. Then in this situation, because you've tuned the learning rate separately at every pre-training step, and because your fine-tuning data set is sort of amenable to this decrease in learning rate that happens as you continue to pre-train for longer and longer, you won't see the catastrophic overtraining effect. And so you can see that the hyperparameter tuning and what you choose to tune against is extremely important for whether or not you will see this curve or not. And you can imagine that if you've done a lot of tuning, that you can get some of the noise by jumping between these curves. And so, in fact, that's what happens in practice. This is the real, well, this is for Sika, but there's like, if you look at all of the graphs for all the data sets, they're all like relatively clean U-shaped curves. That when you do fine tuning, you'll just sort of jump between these lines because of noise or whatever. So you get noise sort of because of the tuning of the learning rate. And so together, this is sort of summarizing what we just saw, is that depending on how you're tuning your learning rate, that's like our title, you can get degradation, or if you can decrease the learning rate very quickly as you pre-train for longer, so you can use a smaller and smaller learning rate, then you might not see degradation overall. And so beyond fine-tuning, just some sort of like other literature that connects, there was this paper that showed that if you pre-train for too long and then you quantize your model to something like 3-bit, then you'll actually see the same effect. And so you can think of quantization as sort of like a perturbation. you're perturbing to the nearest quantized point, and so there's some relationship there. And I would expect that sort of any other situation where you get some sort of a perturbation to your parameters, you might also see similar effects.
I think Zach is on that paper.
Yes.
Yes.
Okay, so that's part A. Are there any questions about that?
Looks pretty clean, yeah.
Yeah. Good, because we also should get to part B too. Maybe we can come back to this.
Yeah.
So we only have like 20 minutes. This is a little shorter anyway. So I want to talk about repetition improves language model embeddings by West. And so like, I mean, the title sort of gives away the actual paper.
So we don't need comments.
It's hard but basically, like, I mean, I don't really need to tell you that there are many language model tasks beyond language modeling. So, like, I mean, I hear that you use embeddings somehow in your works. I'm sure you're very familiar with it. You might want to do things like, text similarity, retrieval, classification, clustering, any number of things with embeddings rather than with where like the actual inference of language models might be too slow for this. And so the sort of corresponding structure, I don't need to tell you, is that we can take some sort of an inner product between two sentences and understand some notion of similarity. This is what an embedding is. Don't need to tell you what an embedding is. So the typical pipeline for converting LLMs to embeddings is typically what you'll have is your input or query, and you'll put it through an LLM somehow. And this LLM has not been trained, might not have been trained explicitly to do embeddings, at least might not have been pre-trained explicitly to do embedding. Maybe it has been, but a lot of times it hasn't. And then you want to convert it to an embedding somehow. So how do you do that? Well, it's really simple. I mean, again, I don't need to tell you this. You just take all your text, you project it through your language model, you take some intermediate state. I mean, oftentimes this is the second to last layer, sort of the hidden state right before you go through the logits, but you could do others too. I mean, there's plenty of papers looking at different strategies for this. And somehow you aggregate all of the information together. That could be something like taking a mean over all of these token embeddings, or doing something else to get a final fixed length sentence embedding. And so what is the problem? Well, causal autoregressive language models these days are the industry standard for many tasks, especially when this paper was being written. And now these days there are maybe like diffusion and other things that are happening, but like causal autoregressive language models have just been so dominant in the space. And so the question is, how can you convert all the money that is being spent on training causal autoregressive models into good embeddings performance? And there's a problem, which is that at least as of February 2024, which is sort of when we were thinking about this, all of the language models that were on this MTED, which is sort of the gold standard leaderboard for tracking performance of embeddings, like 95% of them were autoencoder based. So this will be like the T5, the BERT style models. There's a couple of grayed out ones because in theory we don't know what they are, but I would highly suspect that both of those grayed out ones are also autoencoder based models. And so there was one that's autoregressive, but we can sort of ignore that because this is trained on a bunch. Like they did a lot of, specifically they were generating synthetic data that was very high quality, that was sort of new at that time. And so they get a lot of performance just by adding better data. And so the question is, how do you convert your language model into an autoencoder? And we're going to talk especially like without doing any other training, but you can also do training with this. We'll mention that at the end. And so the idea, sort of based on the paper or the title, is very simple. Like you don't want to embed just I like sunny days in Pittsburgh. Instead, you want to embed I like sunny days in Pittsburgh, I like sunny days in Pittsburgh, sort of repeat it. Maybe with a prompt. Prompt turns out to help. Something like repeat the sentence. And so the idea is just simply, we know that autoencoders were doing extremely well on the leaderboards. So why not take your LM and convert it into an autoencoder, and you can just prompt it to do autoencoding. It works. And so this is sort of magic because that this would work at all, because in theory, the autoencoder that's given the input can just literally copy the tokens. Like it can have a attention head or whatever that just copies the I to the I, the like to the like. And this wouldn't necessarily give you any meaningful information beyond just the token embeddings, which don't work themselves very well. But somehow, magically, this strategy works quite well. And so I want to give you a couple, right, so that it behaves like an autoencoder. And I think the sort of high-level takeaway, which is basically the main takeaway for how to do embeddings for language models, especially autoregressive language models, is that you should really think about sort of what information you want in your embeddings. And in this case, sort of bidirectional information is a simple one, but I think there's a lot other examples. There's another paper that I'll mention at the end that did something similar, but a little different, where if you can prompt your language model so that in the actual token outputs, you're sort of getting the information that you want from your embeddings and maybe even ignoring the information you don't want from your embeddings, this is going to be the way that you're able to convert an LM to an embedder effectively. And so, first of all, like, why does autoregression fail? Well, we can sort of look at some textual examples, and you can look at something like this example. So here we have a query Q. We have a negative S minus, which is sort of an example that if you read that is not the same as the reference. So she loves the summer for the warm evenings. She loves the summer but dislikes the heat. She doesn't like the heat. She likes the heat. These are different. And then you have the positive S plus, which is sort of a rephrase of the reference, where it's semantically the same, but like maybe by the number of like the literal tokens a little bit different. And so if you have an autoregressive model, the second half of the sentence is not able to have any influence on the first half by the autoregressive nature. And so these are going to be represented identically by the LM. If you look at the embeddings of the individual tokens, like she loves the summer. And so in this particular example, if you were to just run a language model that's autoregressive on this example, it might overestimate the similarity of these two sentences simply because it's not able to have the tokens that are early in the sentence be influenced by the semantically different second half. So does last token pooling fix the issue? This might be something you're thinking about. Well, the last token at the end of the sentence has all the information. And so you could just use that. But does that do it? Well, no. Again, you should be thinking about tokens in terms of like, what will the next token prediction actually contain? Like, what information will it have? That's how you should be thinking about embeddings. And the final token here has seen the entire sentence true, but do I have? Oh no, I don't. I guess I do. If you look at like a different example, where again, now what we're going to do is the exact same thing as we did before, except we're going to flip the order. So now the identical parts between the reference and the negative are going to be at the end. So nothing is better than curling up in bed when it's chilly outside. And I love the outdoors even when it's chilly outside, or semantically different, but that last couple words are going to be identical. And so the next token prediction of at least the language model that isn't like doing anything that's sort of like language modeling is going to be biased by the fact that these last few tokens are very similar. And so in this case, last token pooling will overestimate the similarity between these sentences just because the token after it's chilly outside is going to be similar regardless of the context. So the positive here is going to be a little different, right? So we've established the last token will be artificially similar if you just use last token pooling. And in fact, like if you do this repetition that I've been talking about with the prompting, it just solves both issues. So S1, you can think of it as like slide 1. That was like the original example where the dissimilarity was in the end of the sentence, and S2 is like slide 2, where the dissimilarity was at the beginning of the sentence. And you can see that like last token pooling solves some of the issues. I think I might have gotten this backwards. But like last token pooling will solve the issue that we expected it to, but it won't solve the issue that we expected it to not solve. And same with mean token pooling, but both will fail. Like the class, think of it as like classical prompting on some example, and the echo embeddings will work. So this is on synthetic data. It's also true on real data. And so just do a couple results on real data. So one is the 0-shot setting without.
So the echo embedding is a mean tool of the second part. anything else?
Right, so echo embeddings in particular is, yes, you'll literally have this, repeat the sentence, I like sunny days in Pittsburgh, I like sunny days in Pittsburgh, and the underlying stuff will take a mean pool of that.
Like the second to last layer.
The second to last layer, yeah. And so this is the zero shot thing you can do. If you want to then fine tune, you can sort of ablate and decide which is better. I've seen it better in different cases. Sometimes when you're gonna fine tune already, often it's very common to add a special token at the end of the sentence and then fine tune that along with fine tuning the embedding. And so all of this is done with LoRa, which is just, I guess, common in embeddings. But like, you can also, like LoRa by default wouldn't fine tune the embedding, the text of the token embedding. But if you do that, oftentimes you can get good performance. And so you can have like last token pooling with fine tuning networks.
Actually, I have a question. Like,
Yeah.
do you think your previous paper results would be true with LoRa?
The overtraining. So actually, yes, I do. In fact, I don't know exactly. I think there's sort of a solid, intuitively LoRa is like changing less. I know there's some papers saying like it forgets less, but it's still changing by some amount. And I'm going to make up a story here. I don't know if that's true. I could imagine the fact that you're restricting the parameters to like edit fewer parameters or like in like sort of one subspace for LoRa might end up causing you to have to move them more in a certain direction. Maybe, I don't know. I have no idea. Could.
Interesting. I have the opposite intuition.
Okay.
Like, you know, you're basically imposing some regularization and like, so basically, you know, if you're having to find a restricted optimal subspace for the you know, the like weight changes, then, you know, it will be less likely to be the sharp ones, but also like this seems like a very easy to test.
Yes.
And I think, you know, I think the follow-up to like LoRa changes less is like LoRa changes less and it looks less. So like maybe, you know, maybe like, yeah, you get less sensitivity, but that's because you also get less of an improvement.
That is exactly true.
Yes.
Yeah.
Yeah, in fact, when I was doing the TOEFL paper, our initial setup was for unlearning LoRa, but we had to scrap it because unlearning with LoRa was catastrophic. Like we would almost forget everything else. Like when you were unlearning, say, Harry, like a book author which did not exist, it like forget all the other authors. So even though because you merge it, right? I think the blast rate is actually more, even though we think it's less. And so that was a big problem. And we wanted at some point write a paper about it, but such is life. But
Such is life.
yeah.
That's interesting. Yeah, I mean, actually, that would sort of suggest maybe that the overtraining stuff would be amplified by LoRa because it's sort of in order to well, it depends on the task, of course. Right?
Yeah.
But in this case, like the tofu setting, it seems like LoRa is learning more in a sense, like you're unlearning.
So look, me and my intern had a paper
Yeah.
on this, and like basically, if you tune the hyperparameters correctly, there's like no difference between LoRa and full fine tuning.
Okay.
Like there's like scales of this where like if you choose like very low rank, you know, if you have bad hyperparameters, like it moves like, you know, less distance per step or whatever. Like but like you can just train it longer and then you get to the same effect. So like there is like the like LoRa is essentially like the uses for it are, you know, there's lots of like practical uses for it, but like in practice, like eventually you get to the same thing.
So how does this reconcile with like the mosaic paper?
That's my paper.
Oh, that is your
Yeah.
paper.
Yeah, that's my intern data.
I see,
did
I see.
that.
Okay. But LoRa. Okay, I see. If you train it
So
enough.
yeah. So like there's settings in which it like learns less, but like the key takeaway for us was that like given the optimal hyperparameters for both, you essentially they're equivalent.
Okay.
Yeah.
Right. Okay. Cool.
Yeah.
Cool. I think though, that being said, the general trend I would expect to be the same. It might be less, it might take longer, for example.
Sorry, I had a question.
Oh, yeah.
You can go to the slide, yeah. So, if you repeat the sentence, I get how the first problem is solved because you can see the past tokens now. But then how is the second problem solved of like this still being in the end?
Oh, great question. You'll use mean token pooling. You won't use last token.
Okay.
Yeah, in fact, if you do last
that's
token
only for
pooling,
master.
zero shot, it is terrible across the board, no matter what you do in practice. In fact, actually, so like if you look at like this last token, this is like the synthetic data. I mean, it looks a lot like this, generated from like GPT-4. the last token here is like doing well. I could actually find no examples of real data where last token is able to do well, zero shot without fine-tuning. Like last token pooling, you get so much sensitivity from that last token.
So like the end of sequence token that you're talking about is basically to avoid that problem, right? Last token not being a good representation of the last token.
So actually the end of sequence token, what you'd add specifically when you're gonna fine tune. If you're fine tuning, actually all this goes away.
Okay.
And like your model's able to learn like don't output the next token. So if you're fine tuning, as we'll see, like the echo embeddings is gonna have an effect. But it actually turns out that like the last token pooling ends up being better. I think just because you're able to do this fine-tunable embedding. I think that was like a really key part of it, is you have to have the token embedding should be able to be learned. And I mean, intuitively, maybe like that embedding can like learn to attend, like it could implement a mean token pooling if it wanted to. That's something that's sort of more optimal. Right. So anyway, so the idea is here, like, let me just show a couple results of it, just a couple slides more. Is like the echo is doing in this particular benchmark, which is just again this like MTEB, this standard gold, the best benchmark that we have right now for embeddings. Echo is performing like quite a bit better. This is zero shot, so this means no fine tuning. Again, we're using like the mean token pooling with the repetition. Some people have asked in like reviews if like you can repeat more than once and get better performance. No, you can't. Once you repeat once, it's done. You get the bidirectionality once, and then your performance doesn't change. Another is that like you can fine tune, and so like there's a lot of literature on fine tuning. We don't like do anything novel fine tuning wise, but like the general idea is like train with contrastive learning on existing data sets. And here you can expect that, well, in theory, the fine tuning should be able to learn something that's reasonable. In fact, you can even add bidirectional attention. So you can take your architecture and you can just cast it to be bidirectional. You can pretend it was a bidirectional model. It's like the type checks, I guess. And so if you do that, and then you fine tune, the fine tuning doesn't quite get you to, even with bidirectional attention, to the point of echo embeddings. And so in this case, like the prompting alone is able to get you a little bit further.
Did you look at what happens when you do echo with bidirectional attention?
I did not look at that. Yeah, it could be better. I'm not sure.
Well, I'd just be curious if it's worse, because I feel like the intuition I saw. So like I don't know if this might be more recent than this paper actually, but there's a paper Drama out of Meta where they were training on large scale synthetic data, and they were basically taking Llama 1B and then just setting it to bidirectional attention. And they did a bunch of ablations finding, mean versus end of sentence, but this is, heavily contrastively trained. But there was a consistent improvement from, the bidirectionality that one might imagine is from the same property that Echo is solving. And if Echo is solving it better, for example, like the model was not originally pre-trained to be bidirectional and there's some loss there, then I would be curious to see like, would it be better or actually worse? I'm curious if you have any intuition of what you'd expect if you were to take Echo and mess up its attention.
Yeah, I think, okay, intuitively, if you sort of scale data up to be infinite amount of data, the model should sort of learn the right thing to do. And so if it should be doing bidirectional attention, it'll learn that with contrastive learning, no problem. And in fact, you can pre-train these models, of course, to be bidirectional for embeddings, and they do just fine. There was another paper called LLM to VEC, which came out a little after this one. And what they did is sort of took the same idea where you want to convert it to be bidirectional. But what they did is sort of had like an intermediate sort of pseudo pre-training, like a continued pre-training step where they sort of train it to be a masked language model before then doing the embedding step. And they've also found improvements there. And so it seems like at the very least at the scale of data we're looking at, it would help to have some sort of intermediate step, whether it be prompting or whether it be some explicit training to sort of help help transition the model into being a masked language model, a bidirectional model. But as you can see, even in this graph, adding bidirectional attention is definitely giving you an improvement over not. And so you definitely you get sort of multiple tiers of improvement.
Thank you so much.
We are about at time. I want to make sure if there's anything else you wanted to get through here, and maybe you have time for a question after that.
Yeah, so okay, one last thing I wanted to say is another sort of similar idea, sort of similar time as our paper was this paper called Prompt DOL, which is this Jiang et al. 2024. They just said to prompt the sentence, like they literally use this prompt that you see. The sentence, whatever the sentence is, means in one word, and then the next token is like the content of the sentence.
Yeah.
And that worked quite well. I mean, it has a lot more variance than our method over like different ways you can prompt it. So I think we were able to show that our method is a little bit better in a lot of cases. But like it's sort of conceptually the right idea, I think. That's everything. Yeah, questions or?
I'm curious, so like, at the very beginning, you're like, oh, here are all the models and they're bidirectional, except for this one that's the second place. We're gonna ignore it because it's synthetic data. But I'm curious, like, given this like strong evidence that like these models lack this prior, like how is it possible that the data actually made it able to do this task anyways? Like, or like, like that model isn't bidirectional, and like is still doing like the causal language model, it's just like passive learning, right?
Yeah.
And my understanding is like the GPT embeddings, like the OpenAI embeddings previously were also like just taken from one of the GPT models. I have no idea what secret sauce they have. I haven't bought the right people, the right bribes.
Right. So actually, at the time we were writing this paper, the GPT model embeddings were not very good at all.
Sure, of course, famously.
Yeah.
But they were still they were still very widely used, and like until there was like an arms race for INTEP at some point, but before that they were still near the top for like a long time.
Right. Yeah. So I think, I mean, like as you can see with fine tuning, like it's not a huge difference. It's not like a huge performance gap. Like if you can improve, a lot by adding. So it turns out that MTEP, a lot of what they did, and people are sort of seeing this now. I can redid MTEP to sort of address this. Is a lot of the data sort of is designed to be in distribution with respect to the data set. But MTEP is ostensibly sort of an out of distribution data set, but in practice, adding more in distribution data helps. I would guess that if you like actually do an honest comparison on like genuinely out of distribution data, that you'll see a much bigger improvement. Where like, of course, if you like add in distribution data, you're gonna get it.
Sure. I guess my question is less like, is this better? Because
Right.
More like, why does it work at all that this model that has this huge deficit?
Yeah.
Like you're able to train it with synthetic data and get good retrieval. Because like people have benchmarked it outside of MTEP. Like we had like an embedding team that like did a bunch of stuff on our models and did similar training. Like they do retrieve good documents. They're like these monstrosities, 70 embedding models, but like they work.
Yeah.
I'm just curious, like why should it work if there's like this simple thing you can do that makes it much clearer and better, right? I don't know if you have any intuition. You can just like just hot takes.
Yeah. No, I mean, I think that like it's trained on quite a lot of data. Like it's trained on like I think their model was trained on like either 2.2 or 2.5 million examples, which we'll say is like 2 billion tokens, or maybe not quite that, but like order of magnitude-ish.
Yeah.
And so that's like getting up there towards like continued pre-trained scale. I think that it's not that surprising that you can like sort of learn to get a lot of the bidirectionality out of it just by training on 2 billion tokens, or like maybe 200 million tokens or something.
I see.
Yeah.
So maybe like this one final thing about embedding models before we close. Like if you had to like train like a small embedding model today, like what would your like recipe be? Like maybe like would you start with 0.5 billion and then adapt it, like which is probably but also an overtrained model. Like how should we go about it? Should we just do it from scratch, take a model that's seen the world but a bit too much of the world?
So I think today, actually, right now, if you look at the leaderboards, there are some very good models that are very small that are like inherently bidirectional. By that I mean pre-trained to be bidirectional. I think the only reason, in my opinion, that you use a causal model is you already spent a lot of money training it. And I don't know how good Quen is. Quen 0.5. I have no idea. I've never tried it for embeddings. I know that like if it were that much better, like if you didn't want to pre-train your own Quen, like okay, I should say this. If you want to spend the money to pre-train, you definitely do it bidirectionally.
Yeah. One thing I feel is there's something about having seen a lot of data distributions. Like I think standard embedding models might not have seen the depths of internet as much as you think, and the benchmarks might not capture it as well. But
Yeah.
like you might have some very like strange language or like
So
that's I think my main reason of thinking that someone who knows all the distributions can probably adapt it better
yeah,
as compared to an embedding model that was just trained on contrastive pairs available, which is also huge, but maybe not as diverse as the actual internet.
there was also maybe related to this a little bit. There was some like recent work on using a large language model to sort of what they would do is they would rephrase. So you have a document. The problem is this document doesn't have a nice structure. It's also like similarity is really easy to do and it's like a semantic similarity. But when you have some more complicated notion of similarity, like retrieval similarity, where you have a query and you want it to be similar to the document that answers it, it becomes more complicated.
Okay.
And so what they did was they take the query or the document, forget one of them, and they rephrase it synthetically with the GPT in order to look sort of like what they want it to be similar to. And I have to find this paper, but I think that was also kind of a really good idea, which is that if you have a much more complicated notion of similarity than just like a semantic similarity, you might actually need some of this very complicated capability that you get from large models.
Right.
But so there's a new benchmark called Instruct IR on MTEB, which has a lot of examples where you want sort of interesting and odd notions of similarity.
Okay.
And I think that like a lot of the models just entirely fail in that benchmark. And there's been some progress a lot with like larger language models. So in that setting, yeah, you definitely want a large language model.
Because I saw that the MTEP website has gotten a refresh.
Yeah, they did V2.
Yeah, it looks so good.
Yeah.
Yeah. Right. Anybody else? I think we're already over time.
Yeah, maybe with that we can run pause. Thank you very much. And I think technically I am booked